Force, work, and energy review 14. A mass M is released from rest at the top of a slope. It finally comes to rest at the bottom where it is shown as a dashed object. You can see right here on the left, the mass has come to rest. It started up here at the top of the slope. Determine the mass's speed after it has descended a vertical distance h. You can see in our picture here that that first vertical distance h, there's no friction, which means we can use conservation of mechanical energy. So I think all of the potential energy that this mass has up here will turn into kinetic by the time it has fallen a distance h. So that potential energy will be entirely converted into kinetic energy. The mass cancels. V is going to be 2 times g times h square rooted. For the entire trip, how much work does gravity do on the mass? The work done by gravity is always m times g times the change in the height. Well, the change in the height is going to be 2h. And so gravity is pulling downward. The mass is moving in the downward general direction. So gravity is going to do m times g times 2h, because it goes down 2 h's. Gravity does positive work on this thing. Why does the normal force do 0 work in bringing this mass to rest? Well, the normal force doesn't do any work because the normal force is everywhere perpendicular to all of these little displacements that the mass makes as it travels. That's why the normal force doesn't do any work. For the entire trip, how much work does friction do on the mass? And the answer to that is that friction does work that is equal and opposite to the work done by gravity. So that must be negative 2 mgh. And the way we know that is the work energy theorem says that the net work done on a mass will be equal to its change in kinetic energy. This thing started at rest. When it got down to the bottom, it just made it to rest. So its kinetic energy didn't change at all. It was 0 up top, it's 0 at the bottom. Therefore, friction must have done exactly equal and opposite amounts of work that gravity did.